In developing the Nika collider, another advantage of the collider experiment compared to the stationary target experiment comes to mind. Nobody has come up with this advantage so far. For example, to design a fixed target experiment in the area of energies in which modern high-energy colliders work. Such accelerator facilities, generating respective beams, must have a circumference comparable with the circumference of Earth. But what is the fundamental difference between a colliding beam experiment from a fixed target experiment? When a beam interacts with a fixed target, the reaction products are directed forward along the movement of the incoming particle into a thin cone. The higher the energy, the smaller is the gap of this cone. That is why it is an absolutely pointless task, for example, to search for the Higgs boson in a fixed target experiment, because every reaction product would fly strictly toward the incoming beam, and it would be impossible to get rid of the background of primary particles. In case of experiments with relatively low energy, let's say in the energy range used at the Nika collider, it is possible to conduct a fixed target experiment and to design a detector which would perceive the particles generated as the result of this interaction with high efficiency. However, when varying the energy, the spreading angle of the secondary particles will change, and simultaneously, the performance of the detector will also be changed. A collider experiment is free of this drawback. Regardless of the colliding particle energy, the reaction products spread in different directions and may be registered relatively well. The detector has a tiny blind spot which is unavailable for registration, which is directed along the incoming colliding beams. Therefore, a detector could be built, the efficiency of which would not depend on energy. Such a detector would make it possible to intercept almost the entire flux of secondary particles. Why is it important in this type of research, as planned at the Nika collider? It is one of those tasks formulated in a Russian fairy tale. Go there, don't even know where, and find something, don't even know what. Following roughly the same principle, the search for the Higgs boson is performed at the Large Hadron Collider, when various theories predicted different masses of this boson. When universal detectors had been built, the effectiveness of which hadn't depended on energy, and when a program of scanning the energy of colliding particles had been planned, providing the Higgs boson discovery, regardless of its mass in the entire energy range of colliding beams. Roughly the same challenge faces the Nika collider. The Nika collider is meant to discover the signs of newly emerged nuclear matter phase, meaning the boundaries of the state of matter, when quarks, being confined inside particles, are released and a new state of matter emerges, known as the quark-gluon plasma. The task of the Nika collider is to study all the transition processes of quark-gluon plasma transformation. There exist no overlapping theoretical predictions of what should be searched for and in which energy range it should be done, but there is a lot of theoretical works on this topic. When preparing the Nika facility project, propositions from all the leading scientists were collected. They were compiled in the white paper of the Nika project, suggesting research in a variety of phenomena. So far, no theoretician has been able to predict the exact parameters of the event that will show us the emergence of a new phase in nuclear matter. According to its principle, the experimental heavy ion program at the Nika collider is an energy scanning program where each energy needs to have the same systematic error and be able to effectively gather statistics. Besides energy scanning, scanning over the nucleus size is also planned. A collider experiment is one of the most effective ways of carrying out research for such a program. Not everyone shares this view. For example, scientists from Germany, who used to work on the development of the FAIR complex, have decided that the luminosity gain, in this case, outweighs everything else and allows for registration and capturing of more rare events. Scientists from our institute prefer to discard some exponents of luminosity in order to have the opportunity to obtain equally accurate results in a wider energy range.